Bismillahirrahmanirrahim. Today I will start with my lecture on mechanical spring, which is the chapter 10 in your book. So this is, okay, let me just go back and change the color of my pen to green. So this is chapter 10 in your textbook, and it focuses on the springs. There are three topics that I will cover in this presentation. One is the type of the spring, the other is the spring wires and the material of which the wires are made of, and the last one is the material properties of the spring. So the first question is, what is a spring? A spring is nothing, it is a mechanical component. A spring is made in a particular configuration, and the particular configuration here refers to helical configuration. And what is the purpose? To provide a range of force over a significant deflection. That's one. The second objective is to store energy. Store the energy. But these springs are designed in such a way that it can work by a push force, by a pull force, or by a twist force. By these, we'll have the three different types of springs: a compression spring, a tension spring, and a torsional spring. Again, it says the other objective of a spring is to store energy. The springs can be classified into a wire spring, a flat spring, and a spherical shaped spring. So what is a wire spring? The spring which is made of wires. That's a wire spring. What are the cross section of the wire that is used to make a spring? It can be a circular cross section or it can be a rectangular cross section. So if we look at this, in this line, we can see that the wires are used to make helical springs of round or square cross sections. The objective is to resist and or deflect under a compressive load, a tensile load, or a torsional load. And this gives me the three types of springs. The flat springs are, if you look at it, I can make them of using the flat strips, which can be flat, which can be curved. So you can use the cantilever type also, elliptical basically types. It can be wound on a clock type power spring or flat spring washers. And these flat spring washers, which are this, they are also termed as the what you call the Belleville springs. Since we are talking about the two parameters over here in the previous slide and this slide, and those two parameters that we have looked into is that a spring will experience a force and it will deflect. So I have two parameters. One is the force and one is the deflection. The deflection over here we will represent in this one by y. And you know this from your physics that F is equal to Ky. So I can write that the deflection is equal to F over K, or K is equal to force over deflection. This K in physics you studied and you called it as a stiffness. In case of a spring, we call it as a spring rate. So the spring rate is K. And what it is the slope of its force deflection curve. If the slope is constant, then we call it as a linear spring. And you can see this is the same equation which I have written over here. Now we'll see the spring wires made of wires, the wire springs. And this is the focus of this chapter. What are wire springs and how we classified the wire springs further. So wire springs are further classified based on the load that they carry. One of them is called a compressive spring, the tensile or extension springs, and the torsional springs. So a compression spring is the one which takes compressive load. An extension spring is the one which takes tensile load. And a torsional spring is the one which takes torsional load. The compression springs are simple. They do not require an initial load. So if I want to make a compression spring, what I will do, I will just take a rod, which is a solid rod, and I'm going to wrap the wire around it as in the form of a helix that you have studied in your engineering drawing. And if I remove this rod, I will be left with the helical compression spring. So when you look at this spring works under a compressive load. Either I apply load from both ends, or one end is fixed and the other end we will apply a compressive load. This spring in the short form we call it as helical compression spring. The helical extension spring is where the coils are very close to one another. But since it needs to work under a tensile load, I need to have some kind of arrangement over here to pull it, to apply a tensile load. And I'm going to put two different types of combination over here. Here I just put a simple straight wire I will use it to pull it, and here I put a hook which I can use it to pull it, and this is called the helical extension spring. The last one is the torsional spring, in which what happens is that the coils are placed and then I need the two wires at the end in the two opposite direction, such that I can hold this wire and I can move this wire in a clockwise or anti-clockwise direction depending upon the type, the way I have coiled it, and it will have a twisting deformation. It will twist, and that is called a torsional spring. And since it is of helical type, we call it as helical torsional spring. It is closed wound. You can see that they are very, and does not require an initial load. With this knowledge, now we have three of them, and I will show you with the examples over here, the pictures, the true pictures. You can see over here that here we have a helical compression spring. But what you notice, cross section is same, constant. Cross section is constant. The other thing that in this one I just want to show you that the distance between these two is called the pitch of the spring. And you can see the pitch is over here. While this is again a helical compression spring, but cross section is variable. This is a helical extension spring. And you can see all the coils are put together, and then there is a hook here to apply the load. Again, this is a helical torsional spring. Again, it's a closed wound, and you can see that these two attachments over here, and they are made basically to apply the torsional load. These, as if here, they are made to apply the extension load. This is a leaf spring, and you can see over here there are steps, one over another, placed in a certain fashion to make a leaf spring. And this is a disc, a bilevel. You can see that there is a spherical type of shape over here, and which are one over another, and this acts basically as a spring. Here is another picture with different pitch that you can see, different cross sections and constant cross sections. You will see over here the extension spring, different types of ends, short hook, long hook, closed hook, right? Open hook, and all this depends on the application, where you want to use it. You can see again helical torsional springs, and you look at the ends to apply the load, the torsional load, right? And you can see all of these. These basically that you see, this is an end. This is actually the spring. And this is another. This all depends on the application, where you would like to use it and how you would like to basically define it. And these are the different types of the bilevel washers which are used to make basically the bilevel springs. Now we'll go to the second topic about the spring materials. And first I will talk about the material of the wire and its properties, and then we will go into how to determine the material property of a spring. What we need in a spring material? The ideal spring material should have high ultimate strength, high yield strength, and low modulus of elasticity. Right? The low modulus of elasticity high yield strength, and the high ultimate strength. These are the three desired properties in a spring material. The common type of material is the medium to high carbon steel that is used for the maximum energy storage. For dynamic case where the load is dynamic, like the fatigue, we want fatigue strength properties that has to be important. And then based on the type of the duty, light duty or heavy duty. Light duty springs are made from cold drawn or cold rolled, while the heavy duty springs are made from hot rolled or forged forms. There are other spring materials. These you can see over here that the materials of which the spring wires are made of, they are ferrous and non-ferrous. Ferrous, you know, is iron based. While the non-ferrous materials will have the nickel alloys, the spring brass, the phosphor bronze, beryllium copper, and copper alloys. And we'll see in the table on the next slide what do we mean and how we basically look at these spring wires. Now here you see the two different in this table, the two different standards are used. One is ASTM, American Society for Testing of Materials, and the other is the SAE, which is the Society of Automotive Engineers. These are the material designation: A227, A228, A29, A230, A232, and so on. And the corresponding SAE number is 1066. In other words, ASTM A227 is same as SAE 1066. Here we are talking about now material. It's a cold drawn wire. It is called music wire. This is called oil temper wire. This is again called oil temper wire. And you can see at the end here, you see over here, these are non-ferrous materials: spring brass, phosphor bronze, beryllium copper, right, chrome. Now, if we go into the last column over here, which is the description, and that's very important to select a wire to make a spring. So the first one, if you read it, it says A227. It's not expensive. It's a general purpose spring wire. It is suitable only for static loading, and the temperature in which it works is 0 to 120 degrees centigrade. You look at A228. If you want high toughness, this is the spring wire that you use, right? But you will use it to make small coil springs. It has high tensile and high fatigue strength, and again it works in a temperature range of 0 to 120 degrees. But now compare between these two. They are both called oil tempered, but one is good for static loading and the other is good for the fatigue loading. This is not costly, and this definitely costs more, and you can read basically. So in other words, when you want to choose a wire that you want to use it to make a spring, what you need is to select a material from here. But in order to select a material of the wire, you must basically know what this wire is capable of, what kind of properties this wire has, and are you basically looking for the properties which are available in this particular type of material. See this one, this is the table in your book. I think it is table 10.3 if I remember it correctly. This is table 10.3. Now here again you look at it. This is the music wire, right? This is the classification. This is the number. And this is the description. I'm not going to go into the description. I have already explained to you in the previous slide. But when we give basically these number, they are, you see over here, the three numbers. This number you know from ACE, American Society of Testing of Materials. While the UNS is the Unified Numbering System. UNS. That's what the UNS means. And then from this is the series over here. And each series belongs to basically the various metal types. So G from 00001 to G99999. This is carbon and alloy steel. Tool steel is not included. So tool steel is not included. So in other words, when you see this number, you know that it's a unified numbering system for metals and alloys that is used in USA. And this G means it's a carbon and alloy steel. Now you need to go to this number and you will find what are the percentages of the different alloys. And here you will see basically the carbon percentage. What this AISI means. So if you look at it, this number, this AISI is American Iron and Steel Institute, and then it have 4 digits. The first 2 digits define the type, and the last 2 digits define the amount of carbon present in steel. So 10 belongs to one type, which is a plain carbon steel. 10 is plain carbon steel. And this 65 that you see, this is the percent of the carbon which is present, and you can see over here it is between 0.60 to 0.70%. Description is given here, and you can read it and see, is this the wire that you are looking for to make a spring for your application. So for example, if you're looking for shock or impact loading, this is not the one. If you're looking for more than this diameter of the wire, it is not there. So now it's again the description of the material, the other similar specification, and this is the description of the material itself. This is the name of the material. right? Again, the other specifications and then the description. So this is about the wire. But once we know the wire, how do we know what is the strength of the spring itself? Because wire is not used as a wire. Wire is transformed into a spring which is of a helical shape, and that may have a different strength. So the equation that we use basically to determine the strength of a spring material is S ultimate is equal to A over D raised to the power M, where D is the wire diameter, while A and M are obtained from the table. They are given values. So if I will get A and M from the table, but I have to make sure that which material I'm using. Based on that material, I will see what is the diameter of that wire, and then I will select the diameter. I'll put the diameter over here, put the value of A and M, and I will get my ultimate tensile strength. But this is the minimum tensile strength. How we will get basically the torsional yield strength? As you know that you will see it later, that the spring will have the torsional stresses, shear stresses. Torsional stresses are the stresses which are due to the torsional load and which occurs in the form of shear. So the shear yield strength ranges between 35% of ultimate strength to the 52% of the ultimate strength. And we'll see later how we will basically calculate this property. But the most important equation over here is this one. That's the equation. So in other words, when you will start solving a problem, first you have to select a wire. Once you have selected the wire, you know basically its diameter, means its material properties. In other words, you know A and M. Then that wire comes in different diameters. So you will select one of the diameter. Once you know these three, you will be able to calculate the ultimate strength. Now, how to select the diameter of a spring wire, which is required to determine ultimate tensile strength using previously mentioned equation, and what is the link between the spring wire number and the ASTM and SEA number, and what are their other material properties. And this is the couple of slides. So if you look at over here now, this is table 10.4 in your book. This is table 10.4. Now you see over here, this is the music wire. This is the ASTM number. This is the coefficient, the exponent M. And this is the coefficient A. If it is in FPS unit or if it is in SI unit. Right. The diameter in which the wire is available, it ranges from this to this in inch, and it is from this. So let me give you an example. If I choose the music wire, it means I'm choosing A228, and I will say music wire A228 or A228 music wire. And then I'm going to select a diameter. I can select 2 mm, 3 mm, 3.2 mm, 5.2 mm, as long as it is between 0.10 to 6.5 mm. So I know the D. D is known. A, so let's say if I take D is equal to 5 ml. A is 2211 MPa. And M is 0.145. If I know these, I can calculate the minimum tensile strength of the spring material. And once I know that, I can determine also the shear yield strength of the material. This is the table 10.5. So here what is given? It just gives you the maximum allowable torsional stress. In what type of spring? Helical compression spring. What kind of load? In static applications. So if your material is a music wire and there is a 45% of tensile strength, so either it means 0.45 of S ultimate. This means 0.60 to 0.70 of S ultimate. Now before the set is removed, then the value is typically lower. Once the set is removed, then the values are typical higher. Same if you see, if it is a hardened and tempered steel, austenitic stainless steel, and non-ferrous alloys. And in the next lecture, I will tell you what do we mean by set removed, before and after. This is another table by which you can determine the properties, but this is more complex. I just want to show it to you, but you will be using the tables to determine the minimum ultimate strength. Here is the minimum ultimate strength again to determine. Here is the wire diameter and here is the minimum tensile strength. So if you look at ASTM B159, this material, it is available from 0.10 up to this diameter. You choose any diameter and you will get its minimal ultimate tensile strength. And once you get its minimum ultimate tensile strength, then you can determine what is the allowable shear stress by using these equations with the different conditions. Summary, what we have gone through is first that the important thing is that we know what is a spring, what are the different types of a spring, and then in wire spring, what are its classification. And since we know the spring is made from a wire, so we need to select a wire, what kind of wires are available, and their description for what kind of jobs or applications they are suitable. So we need to select a wire and its diameter. Once we have this, then we go and we determine its ultimate tensile strength, minimum ultimate tensile strength. That's for the spring. So table 10.3 on page 516 gives materials name and description. Table 10.4 gives constants A and M to calculate minimum tensile strength of common spring wires. Table 10.5 gives you the other mechanical properties like E and G, as well as the what you call cases for where you have tension or torsional springs. And the last one is to provide you the allowable torsional stresses for helical compression springs under static load. That's it for now. I will basically send you the second one, and then will have the third one. There will be 3 lectures on the spring, and then we will have the fourth one on problem solution. Thank you very much.